Thank you, Ivan. Good afternoon, everyone. It is early morning, but I will try to do my best. So I will give you overview of 3 research topics which are all around active matter. Some of them will be chiral active matter, and I will speak not about collective properties of active matter, but about individual constituents, like individual building blocks of this active matter, and how can we control and manipulate those individual blocks. So in this outline, I show you these examples of 3 systems we considered. So we start from active liquid crystal skyrmions. So what you see here is nice experiments from Ivan group, where you see a top view in polarized optical microscopy of one liquid crystal soliton or skyrmion, which is moving forwards or in one direction, in another direction, and you can change this by modulation voltage, which is applied across the cell. So you can reconfigure this individual building block of active matter, one individual skyrmion, by applying voltage of different frequency. In the second part, I will speak about new effect which we discover on chemical nanosphemers. For example, we can control their motion by placing these active nanosphemers in certain non-homogeneous environments and actuated by certain type of forces. This system could be of relevance for chemically active enzymes. And the third example I will discuss are chiral thin platelets. You see here 2 gold platelets, which are around 100 microns, 10 microns across and 100 nanometers in the width, and they are actuated and brought to a spinning motion by ultrasound. So I will discuss how this motion depends on various parameters. So these are 3 topics of my recent research, which I am going to discuss today. So let us start from liquid crystal skyrmions and active liquid crystal skyrmions, where activity is imparted through coupling the liquid crystalline material to electric field. So first of all, let me briefly remind you what is a skyrmion. So this is a beautiful picture from Paul Ackerman and Ivan Smaluk paper, where you see a classical 2-dimensional configuration of the director field vectorized, or if you wish, magnetization field in 2 dimensions. So you see here color-coded representation of the 2-dimensional director configuration. And what is important here, that from the center of the structure, which is color-coded in red, in all radial directions, the director exhibits a twist by 180 degrees. And now if you would map these configurations to other parameter manifold, which for magnetization field or vectorized director is 2-dimensional sphere, you will realize that this mapping would cover the sphere completely once. So all points on a sphere would be visited, or all orientations are realized in these 2-dimensional configurations. So we say that this mapping of this vectorized director onto the sphere S2 will cover it once. So what does it mean from the mathematics point of view? It's that it is not possible to deform this configuration to a trivial uniform one without cutting and introducing some discontinuous jumps. In that sense, mathematically, this structure is topologically protected. But for chiral liquid crystalline magnets, this structure in some situation corresponds also to the ground state, not only topologically protected, but also physically the most stable configurations. So why do we care about these skyrmions or solitons? So first of all, due to their stability and topological protection, they behave like a quasi-particles. Moreover, they can even be brought to a motion. But before we come to the motion of the skyrmions, let me briefly explain you how we can realize these systems or these skyrmions in three-dimensional configurations. Experimentally, these particles or these quasi-particles are realized in chiral liquid crystals, which is placed between two plates. So how can we introduce this non-uniform structure between two plates? So experimentally, the plates are usually imposing homeotropic boundary conditions. So in this right panel, schematically represented by this gray arrows pointing upwards. So how can you now introduce this non-uniform topologically non-trivial configuration between these plates with homeotropic boundary conditions? So first, imagine this baby skyrmion, which is represented schematically at the bottom of this double twist cylinder, and then you develop it along the symmetry axis into a third dimension. So just translate it uniformly. You obtain the so-called double twist cylinder. And then in order to place this double twist cylinder between plates, you squeeze the top and bottom portion of cylinder, decorate it with the hedgehogs, which is schematically represented by these red points. And in this way, you manage to introduce smoothly this structure into uniform background. And these points, they are self-compensating hedgehog defects. So in this configuration, which is studied intensively in Ivan's group, is called toron. It's a three-dimensional structure. So in these torons, their size is typically given by the cholesteric pitch, which is of the order of the thickness of experimental cell. So why do we care? What is interesting about this system? So there is a way to bring this into a controlled translational motion. So a schematical representation of experiments which Ivan uses in his group, there are two plates, glass plates, for some distance. And here in the middle plane, I show the configuration of the director field when there is no electric field applied. So in the middle, we have a red color region where director is pointing downwards, and at far field, director is pointing upwards, indicated here by the blue arrow. And then in between, there is a twist by 180 degrees. So this is a configuration axially symmetric without any field. And now when we apply field on the right panel, electric field, which schematically is illustrated by this stepwise pulse width modulated profile, at sufficiently strong voltages, the far field director from the vertical orientation morphs to the horizontal one, which is indicated here by green arrows. But this morphing or this changes preserve topology. So topological structure of this configuration is preserved in the sense that the mapping, which we discussed earlier, mapping from the real space to the ODE parameter space does not change. But what is interesting, if you now change frequency of this voltage modulation, you can achieve motion of skyrmion, and the direction of motion depends upon frequency. So you can achieve motion towards, let's say, right for low frequencies or towards left at higher frequencies, right? And this is very curious and very interesting effect. We have a quasi-particle which moves through the liquid crystal matrix, and you can control this motion by the electric field. But it's not the end of the story. This system, as Ivan showed, exhibits fascinating collective out of equilibrium behavior. So in this video from Ivan's group, you see a collection of 29 torons which form different structures from linear chains, like in this realization, or compact clusters. And you can change this behavior just by tuning modulation voltage. For instance, in this experiment, the modulation voltage was changing between 2 to 8 Hertz. And just by changing this voltage, you can modulate interactions between these torons and obtain linear or compact clusters. So this is one of the goals of our research in my group. We try to understand the collective behavior and the underlying effective interaction between these objects. So how can we, first of all, understand the motion of these particles? So in Ivan groups, and also in my group, we used as a first step so-called fine-grained model, which is in this case a standard Frank-Osin elastic free energy. And then we can minimize the full continuum Frank-Osin elastic free energy for the experimental matching condition and try to look upon the formation of the director field. So what I show in this right panel, it's a cross-section through the three-dimensional cell where we see this starting configuration of skyrmionic type. You have the central red-colored region where director points away from the screen. So the color code represents the Z component of the director field, the component perpendicular to the screen. So the blue color corresponds to the director pointing towards the screen, and this transition is a twist region. So this configuration here corresponds to the point 0 on the left graph. And so on the left graph, I will show the displacement of this red colored region as a function of time. So displacement here, delta x, is measured in units of the cell thickness, and different curves, we have 3 curves, corresponds to different ratio of pitch to wall thickness. And this parameter gamma here, it's a rotational viscosity which enters into the Frank-Osin relaxational algorithm, and K is the elastic constant. So this is displacement when we turn field on and off. So now I will start playing this video, and this displacement corresponds to moving upwards on a field on branch. And then when we completely relax, we turn field off, and the skyrmion returns slightly back. However, there is an offset. There is a net displacement during one on and off cycle of the field. But important here to realize that we allow skyrmion to completely relax. So we reach a steady state, stationary equilibrium steady state, or not steady equilibrium state, and then we turn field off and skyrmion relaxes back. So, and this is like a main mechanism of achieving translational motion, this asymmetry. So the on curve and off curve, they are asymmetric in a sense that director relaxes towards equilibrium state in a different non-reciprocal way. And we can exploit this asymmetry, this net offset, to control frequency or to choose frequency and to control velocity of skyrmions. For instance, in this slide, I show now the situation where we subject the skyrmion to a pulse width modulated electric field. So these curves corresponds to the displacement of skyrmion at various periodicity, here given by these numbers, periodicity of this pulse width modulated electric field. And you see the different curves which corresponds to different periods have different net velocity. So after initial transient, we then reach finally a steady state when skyrmion moves at constant net velocity. So in this video represent the three-dimensional simulations of a net motion of skyrmion, and this video corresponds to the black curve, which moves at the highest frequency. So in this, simulations have been carried out in the group of Ivan Smaluk. They nicely reproduce experiments. Ivan also looked upon other properties of the director field, like a region of the maximum twist deformations, and he nicely showed that this motion is accompanied by the non-reciprocal deformation of this twist region. So this, as we call fine-grained or full-scale model, explain experiments. However, it is very complex, and the question we ask, what would be the most minimal, the minimalistic model which would qualitatively describe the motion of the skyrmion? So what is like a basic parameter or collective variable or variable which would nicely encode and represent motion of skyrmions? So then we propose this so-called collective variable model for dynamics of skyrmions, which is based in general just on 5 collective variables. So we start from this very simple two-dimensional ansatz for the director field around skyrmion, which depends on the position R. And these parameters are the 3 collective variables. Psi will be the width of the twist wall around skyrmion core. So in this right panel, I depict the polar angle psi, which characterizes the director field of this axially symmetric skyrmion. So the director field is parameterized by this one angle psi, which depends on the distance r from the skyrmion center. So 0 corresponds to the skyrmion center. Then there is the constant shoulder of the width pi over 2. There is a twist region in this angle psi of the thickness lowercase psi, where director changes from the vertical pointing upwards to vertical pointing downwards, and the thickness can change, right? So the analytic expression for this curve, which describes the axisymmetric skyrmion, is given by this long formula. So we have here 1 is a step function, pi is a pitch, and this is a Gaussian. So the Gaussian, which is measured with respect to the skyrmion center, pi is the pitch, and psi is the width of this twist region. So I will show you that this parameter is important one, and when we cycle electric field on and off, the width of this twist region changes, imparting translational motion. So this is a configuration of the skyrmion, which has their 3 parameters: width of the wall and the RS, which is the center of skyrmion. So beware that RS implicitly sits in the definition of this 0. So we measure the distance from the center relative to the skyrmion center. So this is a configuration at no field, right? So what about the cases when we apply field on? How we can model the deformation or morphing of skyrmion at field non-zero? So this enters through far field director. So let's start at 0 electric field. At 0 electric field, director is pointing along z direction, vertically. When we apply electric field, this far field director starts changing in response to electric field. In general, we can represent the far field director by this simple spherical coordinate representation, where we have two angles: polar angle theta, capital theta, which depends on electric field, and azimuthal angle phi. So these 2 angles, capital theta and capital phi, would be another 2 collective variables which represent our skyrmion. So this is the far field director. So what about the local field of skyrmion? We assume a simplest possible approach. We assume that at non-zero electric field, that initial axisymmetric ansatz rotates uniformly. So then the director field, denoted by letter n, which depends on the coordinate, and on the 5 parameters, capital theta, capital phi, which are representing far field director. Psi, it's the width of the twist wall, and RS is the center of skyrmion, is given just by rotating this axially symmetric ansatz by some matrix R hat. And this rotation matrix is constructed from the condition that it rotates far field background D to this deformed or tilted configuration N0, which depends on E. So basically, we locally rotate director by a given angle. So, and this is our model. So we have in general five collective variables. However, not all of them are relevant. If we, and here in this cartoon, I represent configurations, this morphed configurations of skyrmion at various conditions. So the panel A corresponds to the zero field axisymmetric skyrmion configuration, where background pointing upwards, away from the screen. Then there is some tilt of the background by 45 degrees. And you see that the structure resembles that observed in experiments and in 3-dimensional simulations. And the panel C corresponds to the maximum tilted far field background, where background just lays in plane, and this configuration has a right and correct symmetry in a field on state. So now our goal is to construct dynamic equation for these parameters. We have 5 parameters, so we want to construct dynamic equations. But not all of 5 are relevant. For instance, if we assume that electric field lays in the y and z plane, so if you assume our electric field has this form, where this capital E is the real field, and this capital W, it's a fictitious field. Why we need this fictitious field? I didn't tell you at the beginning. This model we construct for a 2-dimensional system, while in experiments we have a 3-dimensional system with homeotropic boundary conditions. So this will mimic effect of strong boundary conditions. So when we select electric field in this form, it turns out that only 3 collective variables are relevant, which I denote by capital X. Is the polar angle theta, which depends on electric field and time, twist wall, and X coordinate of the skyrmion center. The Y coordinate of skyrmion center doesn't change. And the capital phi, the angle, azimuthal angle of the far field background, will align fast into the plane of electric field and will stay constant. At this selection of the electric field, the azimuthal angle of the far field background will be always minus 90 degrees. And now, what about dynamics? We want to write dynamical equation for these variables. We have 3 collective variables. So we just use the balance of force. We balance dissipation and elastic forces to construct the dynamic equation for this variable X. So dissipation forces are given by the time derivative, by the derivative of the dissipation function with respect to the rate of change of this coordinate. So this first derivative is just the dissipative force due to the reorientation dynamic of the electric field. The second derivative is just elastic force, where F with sub FO is a Frank Austin elastic free energy. So what we need to do? We need to take this dissipation function, which is given in dimensional form by this simple integral. It's just the integral of the square of n dot. So then you need to substitute the director ansatz into the dissipation function. You substitute ansatz into the Frank Austin free energy. You carry out integration with respect to spatial variables, and then you write equation for this dynamical variable. So some of them can be presented analytically. Some must rely on some numerical work. So the most relevant equation for us is the rate of change of the coordinate position. So the X coordinate of skyrmion has this simple form. Some numerical prefactor C of order of unity. Xi is the dynamical variable quantified twist wall thickness and rate of change of the far field background. So this product basically quantifies the velocity of skyrmion and nicely links the net dynamics of skyrmion to this intrinsic variable. So Xi is the intrinsic variable of skyrmion, and theta is the global variable which quantifies the far field director. So when you see that velocity is at largest when the rate of change of the far field background at highest, right? So this equation for theta dot we can solve analytically, while Xi is not doable analytically, so we obtain it numerically. So now the question is, what is the velocity of skyrmion, let's say, at some protocol of driving electric field? For instance, if we have the electric field of this pulse width modulated form, when we have on and off portions of a certain duty cycle, where duty cycle is the duration of the on period to the whole period of the modulations, and we select electric field in this form, right, where E points to negative Z direction and W, as I told you, just effective anchoring, models effective anchoring. The question is, what is the velocity? So the typical translational velocity of typical coordinates of skyrmion as a function of time is shown in this slide. for some selection of model parameters. So at some initial transient, which are 2 or 3 periods, the skyrmion reaches a steady state and moves at a constant velocity. The velocity is given by slope of this red curve. So the one period from point A, B to C, over one period, you will achieve a net displacement delta x, right? So this is the on branch of a skyrmion motion when field is on, and from point B to C, there is an off branch. So you see that the off branch has the larger relaxation time compared to the on branch, which is not what experimentally is observed, and is related to the selected way of the electric field. But what turns out from our analysis, it is instructive to look upon trajectory of skyrmion not in the real space, but in the phase space given by these intrinsic variables, psi, which is a twist wall, and theta, which is a polar angle of particle director. So this trajectory, starting from 0 and going along this curve, corresponds to the real space. So after a short transient, like a 2 or 3 oscillations, we reach this orbit, steady state cycle, so-called, where skyrmion cycles along this orbit indefinitely, as long as field is cycling. It's an off branch and on branch. So, and why this orbit is important? It turns out that the net displacement delta x is given by the area enclosed by this orbit, right? So we can define the psi average of a branch on and average of a branch off. So if you define psi average over the theta, we can express net displacement just as this simple product is the range of background angles from theta b to theta a. So it's a range of background angles spanned through this one period, and the difference of the on average psi minus off. So the simple formula expresses the net displacement and links displacement of a skyrmion over one period to this intrinsic variable psi and global variable theta b. And now you divide this delta x by the period and you will get velocity, right? So our model nicely explains the links between this intrinsic variable psi and the net displacement. We could also figure out conditions for the reversal of the skyrmion motion. For instance, in order to observe reversal, we need to change our driving protocol. So this is a driving protocol, electric field, which has this electric field pointing into a negative y direction. We have this our effective anchoring, but we must add an extra electric field into the z direction, which time dependent and in antiphase with the y component. This is needed for the reversal of the skyrmion motion. And now left panel show you the color-coded velocity of skyrmion depending on the duty cycle of this electric field and the frequency. You observe a nice reversal of the skyrmion motion at all frequencies when you change duty cycle. And then we can compare velocity qualitatively, velocity of skyrmion on the upper panel. On the upper panel, I show you velocity of skyrmion from our simplified model as a function of frequency. And at the bottom panel, it experiments from Ivan's group. So qualitatively, the shape is very similar. We have the 0 point, we have a global minimum, and so on. So the summary here is that simplified model relates the motion of skyrmion to this one unique collective variable, which is psi, which is the thickness of the twist wall, and the rate of change of the far field background. And then the future work in this direction is to generalize this model to many particle systems. Now I will switch gears and come to another topic, so-called mechanochemical active ratchet. I will explain all this word clearly to you. So first of all, what is a ratchet? Ratchet is an effect which exploits out of equilibrium thermal fluctuations and spatially non-uniform environment to achieve directed motion of Brownian particles. The known example is so-called passive Brownian ratchet. When you place Brownian particle in this axisymmetrical potential, and then when you add on top some time-dependent forces, you can achieve rectification. You can achieve a net current of Brownian particles under this condition. So this time-dependent force makes system out of equilibrium, and this combined with the spatially non-uniform environment will lead to the net current. Another example is so-called active ratchet. When you have this non-uniform potential, spatially non-uniform, non-symmetric, and you have an active Brownian particle, not passive, but active. So what is the difference? Active Brownian particle exhibits self-propulsion. Then, for sufficiently high self-propulsion velocity, this active particle will exhibit, again, rectification or motion along this ratchet potential in a certain direction. We discovered a new novel effect, which is not exhibited by these two past examples, so-called active nanoparticle, which is placed in this ratchet potential. And then this active nanoparticle, when it is not acted by any other additional forces, will be sitting happily at the minimum of this potential. But now if you take this ratchet potential and add on top of it a transverse force, so the force which is pointed towards the screen along this grooves of the ratchet, we will achieve rectification of these nanoparticles. What is important that this mechanism discussed in this part is not operational for passive Brownian particles or for standard active Brownian particles. So it's a novel mechanism which is exhibited by a certain class of active nanoparticles, for instance, like catalytic enzymes, right? So one example experimental for which our mechanism, rectification mechanism, will be operational are these, let's say, catalytic enzymes. There are experimental evidences which shows that active enzymes, like in this example, ureas, which is in the presence of substrate urea, decompose urea into ammonia and other products, exhibit self-propelled motion, which is showed by the enhanced diffusivity. So experimental evidences, basically single particle tracking experiments based on the total internal reflection microscopy, shows that when you take this catalytic enzyme, in this case ureas, and place into the substrate, let's say 1 millimole of urea, this color-coded trajectory, it's a single particle trajectory tracked by microscopy, and then in the presence of the substrate, trajectory is much more spreaded compared to the case when the enzyme moves just in a buffer. Then you can quantify these trajectories in terms of mean square displacement. You can plot mean square displacement of these enzymes as a function of time, where the red curve would correspond to enzyme moving in a buffer solution, and the blue curve and symbols would correspond to the enzyme moving in the presence of substrate urea. Experiment shows significant enhancement of this diffusion coefficient. So these experiments are usually interpreted in terms of active Brownian particle model. So we suggest that this ureas catalyzes reaction, and each reaction leads to the net displacement in a certain direction, which can be then represented by the self-propulsion velocity. And then the simplest model of this active motion is the so-called active Brownian particle model, where you have this Langevin equation. Velocity of an active particle is given by this self-propulsion velocity u along the director of the particle given by vector n. In general, you can have an external force which acts upon this particle with the mobility mu, and the last term represents a noise. So this is a standard model of the active Brownian particle where activity is encoded in this parameter u. You solve this equation and you find the net diffusion coefficient or long-time diffusion coefficient d of active Brownian particle is enhanced compared to the passive case. So d is the diffusion coefficient of the passive particle, and u square would be self-propulsion velocity, and dr is the rotational diffusion coefficient. So indeed, if your particle is active, moving with the speed u, you will observe enhancement of the diffusion coefficient. However, as we realized, this model is incomplete. this model is incomplete and thermodynamically inconsistent. The one ingredient very important, what is missing in this model, we have direct reaction. But what is missing here is the reverse one. As we know, Onzager told us that all thermally activated reactions have the reversed one, right? This is the basic principle of microscopic reversibility. So we generalize this model by including this missing ingredient. So we have here a cartoon, our active enzyme, which can move along director N. And there is a reaction, forward reaction, which takes a substrate by this, represented schematically by this red dot, transforming it into a product. And we add also the reverse step, so closing this reaction loop with a rate K minus. So the reverse reaction can also occur based on the principle of microscopic reversibility with the rate K minus. So we have a forward reaction rate with rate K plus, which translates this enzyme by delta R into a N direction. Along the N direction, we also include this backward reaction with rate K minus, which translates our particle in a negative direction. And then rates are not arbitrary. Rates must obey this so-called microscopic reversibility or local detail balance. The rate of reaction are given by this Boltzmann factor, where delta G is the free energy of reaction. So each reaction releases free energy delta G. And this term delta W is the work done against force. We apply a force upon our particle, and we then must include this work. Now, the key point here, you have a work, which is a mechanical concept. And on the left-hand side, you have a reaction rate, which is a chemical concept. So we have a coupling between work or mechanical forces and chemistry. So this microscopic reversibility realizes this mechanochemical coupling. This means that this nanoparticle or velocity, active speed of this nanoparticle, UA, becomes dependent upon environment. So the chemistry or reaction rates probe the potential landscape. And then generalized Langevin model is formulated in these terms, where now U, self-proportional speed, is not constant, but is stochastic random variable, which reflects this fact that reaction rates forward and backwards depends actually on the active force, depends on the external force. There are also fluctuations. So this Markov process, random jump process, can be represented in the continuum limit. So in continuum limit, we can write this active speed in a very simple form. This active speed in the continuum limit, when the jump of the nanoparticle is very small, there is three terms. Is the constant net velocity VA naught, which is just a difference of reaction rates without force multiplied by the jump. And the most important term is this one, where we have the force dependence explicitly changing this active speed. So this Fn is a projection of the external force upon direction of motion. This parameter dA, it's a so-called diffusivity of activity, quantifies their fluctuations of the reaction forward and backward. And the last term is the noise. So you see that in this thermodynamically consistent model, we have the dependence upon external force. Velocity of active particle explicitly depends on the external force, and there is noise. And when we solve equation of motion, Langevin equation, with this generalized active velocity, we find the diffusion coefficient with two extra terms. So this is the old term present in the standard Brownian particle. This is the enhanced diffusivity due to the constant average self-propulsion velocity, but there are new terms. This one is the most interesting. So there is the enhancements of diffusivity proportional to the external force F, which is not typical. You apply a constant force, let's say at X direction, and you observe symmetric isotropic enhancement of diffusivity proportional to F squared. So this is direct consequence of that mechanochemical coupling when your chemical rates can be controlled or tuned by mechanical forces. And now we can exploit this effect to achieve, what we call it, mechanochemical ratchet effect. So we have this nanoparticle, chemically, microscopically reversible nanoparticle, and now we place it into this ratchet potential. So on the top you have a formula, and the red curve corresponds to this ratchet potential, which is periodic and axisymmetric, and not symmetric. So it's slightly tilted, right? So we place nanoparticle in this landscape. And now what is interesting here, if we now apply to this nanoparticle force transfers to the ratchet, so shown by this arrow F perpendicular. So basically you take your ratchet and push particle along the ratchet grooves. So you push particle along this ratchet grooves at constant velocity F perp. If parameters are right, which meaning if this actuation velocity is large enough, the particle will start moving in a certain direction. And this effect is only and only observable within this thermodynamically consistent model. So we can calculate the net current along the x direction as a function, let's say, of the amplitude of this transfer driving. This curve shows you the velocity, net velocity along the x direction as a function of this transfer driving for different realizations. So different curves corresponds to different depths of this ratchet potential. So what is interesting, you have this optimal transverse driving at which the current, absolute value of current, is maximized. And then this dashed curve at zero net current corresponds to a standard Brownian particle. So this effect is only appearing when we take into account this microscopic reversibility, and it is not exhibited by the standard active Brownian particle. What is interesting, our result demonstrates that the location of this minimum depends sensitively upon the system, basically upon the activity of the nanoparticle. So you can have different enzymes which exhibit different activity, different turnover reaction rates. And those two types of particles would exhibit different location of this optimal maximum speed current. So this mechanism allows you to sort your active nanoparticles based on their activity. So how can we rationalize this result? So it turns out that our active nanoparticle model can be mapped onto a much more simpler case, passive Brownian particle. So this equation represents a Langevin equation for the coordinate x of the passive Brownian particle, which is, however, subject to a stochastic force. So the first term represents a stochastic force. Why stochastic? Because it's angle phi. It's an orientation of our nanoparticle which undergoes rotational Brownian motion. So this phi is an angle of nanoparticle, like orientation of nanoparticle, which is a random variable, and amplitude is given by this transverse drive, right? So this is stochastic force acting upon passive Brownian particle. The third force is a regular force due to the ratchet potential, and mu tilde it's a mobility, and the third term is just a noise. So we have a Brownian particle moving in a ratchet potential subject to a stochastic force. So if amplitude F perpendicular is large enough, and if orientation of our nanoparticle in the right direction, then this term, which is coming from this activity, can beat the regular force and the particle can hop through the minimum. So this is like our basic experimental, qualitative explanation of this effect. What is more, however, interesting, if you take this nanoparticle and start acting upon in a transfer direction, start acting upon this nanoparticle by oscillating force with certain frequency capital omega, we observe a multiple reversal of the current. So these curves represent a net current of active nanoparticle along the ratchet potential in the x direction, the function of transverse force amplitude depending on the angular velocity. And if not angular velocity, angular frequency of this transverse driving. So what is interesting, we find this reversal of the current. Particle can move leftwards or rightward depending on the amplitude. And this is again can be exploited to sort these active nanoparticles in this ratchet potential. So at this point, I would then switch gears and come to the third part of my talk. It's about ultrasound-powered microspinners. So the experiment, our combined theory experimental work was motivated by this nice experiment where they showed that if you place a nanorods into an acoustic chamber, so we have here acoustic chamber, right? Transducer which excites oscillations of this resonator wall, and this is a liquid environment in which a nanorods are dispersed. Acoustic sound waves is reflected from the reflector wall, and then you have a superposition, and the system parameters are tuned in such a way that a standing acoustic wave is formed into the system. Then these nanorods acted upon the acoustic pressure would accumulate into the mid-plane, where nodal plane of the standing acoustic wave, and we'll start exhibiting this nice, as you will see on the next movie, translational motion. So you see here this nanorods, which are basically bimetallic nanorods, non-symmetric along their axis. They accumulated at the central plane of this acoustic chamber, where the pressure is zero, and they exhibit this translational motion. So our goal was try to achieve a more interesting motion patterns, namely spinning motions. So we designed, in collaboration with our experimental colleagues, this so-called twisted star-shaped particles, which are shape of which is characterized by two parameters. We call it chiral asymmetry C. So when you change this parameter C, you can interpolate between, let's say, left chiral particles and right chiral particles. And there's another model parameter, rotational symmetry N, which quantifies how many of these features you have on your particle. So it's a rotational order symmetry. And these parameters, C and N, are our design parameters, which enters into the simple parametric expressions, which quantifies the shape or perimeter of these nanoparticles. So these nanoparticles, nanoplatelets, were synthesized by the ion deposition techniques, were composed of a gold. They are very thin, of the order of 100 nanometers, and lateral size of order of 10 microns. And now the question is how the motion of these objects depends when we place them in that acoustic chamber, right? So here the experimental setup, we have our resonator wall, reflection wall. The thickness H between these walls is tuned such that just half a period of acoustic wave fits between this wall. So when under this condition, we form a one standing wave with a nodal plane just in the middle. So acoustic pressure forces these nanoparticles into the mid-plane, and they are all moving in the middle plane. They have no chance to flip their orientation. In that sense, they are two-dimensional chiral objects. So this video shows you a motion of two examples, left chiral and right chiral, as we call spinners, moving in an opposite direction, right? The question is, first of all, how the motion depends on these various shape parameters. And the first graph shows experimental quantification of the angular velocity. So the vertical axis shows the angular velocity of spinners depending on the chiral asymmetry C. We change chiral asymmetry from the -3 to +3, and the rotation sense changes from the clockwise for -C to anti-clockwise. So the different symbols correspond to different particles, and the solid circles are just mean. So this result is not very surprising. You have a chiral object, and under driving of the acoustic pressure, so you would expect this. It's not so surprising. And then the particle, which is chirally neutral, would not exhibit any motion. However, what is more surprising is the dependence of the angular velocity upon this order of rotational symmetry n. So what is here important is this feature, reversal of the motion by changing this parameter n, let's say from 3 to 4. This is very interesting. You have all conditions kept constant, but you just change this rotational symmetry n from 3 to 4, and then 5 again exhibit unusual sense of rotation, and then it's again a reversal. So this multiple reversal of rotational direction is very unusual and challenging to explain. So our role was try to understand what is then going on here. So these particles with four fins, they spin in the opposite direction as is expected for particles with 3 fins. So my role was to build a model which explain this experimental result. So what is the mechanism of this motion? So mechanism is related to so-called asymmetric acoustic streaming. Acoustic streaming, it's a phenomenon known in a fluid dynamics for a long time. Imagine you have a sphere, small sphere or cylinder, which is oscillating at high frequency in the liquid. Or alternatively, you have a stationary sphere, which is subject to an oscillatory ambient flow. And then these streamlines are steady state pattern in this flow field. Key point here, steady state. So you oscillate your particle at megahertz frequency and you observe this steady state flow pattern. And we believe that by changing the shape of our particle, we can pattern the structure of these acoustic streamlines and control the motion, resulting motion of these nanoparticles. So our model is very simple. So we start from just a very thin plates placed into the ambient fluid. There are parameters of our particle thickness, radius, and there is the acoustic field applied far away. So there is the sine wave applied to the fluid, and then the goal is to figure out angular velocity omega. What is angular velocity omega, right? So the model which describes motion of fluid is this Navier-Stokes equation, standard Navier-Stokes equation, where you have a fluid velocity u, you have a density of fluid, pressure in the fluid p, kinematic viscosity, and incompressibility condition is imposed, right? Then there is a boundary condition. Boundary condition, non-slip boundary condition on the surface of the spinner. The particle spins with unknown angular velocity omega. So this is a non-slip boundary condition imposed upon the fluid. And there is the boundary condition at infinity, just describing these oscillations due to the acoustic wave. And then to find out omega, you must impose condition of no net torque. You must find solution to this equation such that there is no net torque acting upon our spinner. So this will give you the omega, a known angular velocity. We dimensionalize this equation to find out what are the relevant parameters. We can write this equation into dimensional form. And there are two main parameters, so-called frequency parameter lambda and Reynolds number. All rest are dimensionless. It turns out these two main dimensionless parameters which control the system behavior. So experimentally, Reynolds number is in the range between 0.4 and 1.6, so not very small. And this frequency parameter lambda, which basically controls the ratio between the size of the particle and this square root I will show you, is the width of so-called Stokes boundary layer around the nanoplates. Experimentally, this parameter in this range. So although Reynolds number is not very small, we resolve to the perturbation solution of this equation, assuming Reynolds number is small. So we solve this equation perturbatively. We expand velocity, pressure, and stresses in Reynolds number and just consider the leading components, U0, and the first order component. Important to realize that angular velocity is the first order in Reynolds number. So we solve this problem perturbatively, and I will show here the qualitative solution. So this is a zero-order solution of this perturbation analysis for several instances of time. So time grows from the left to right and from the bottom to the left to right. So what is important here to realize? You see formation of these so-called vorticity layers around the particle, so-called vorticity boundary layers, or so-called Stokes boundary layers, right? So the size of these boundary layers is given by the ratio of kinematic viscosity and the frequency of the acoustic field. So by changing these parameters, which enter this ratio R over square root this lambda, so by changing this lambda, you basically change the size of the Stokes boundary layer. And when the Stokes boundary layer becomes comparable to the thickness of the plates, then the interesting phenomenology happens. Then this Stokes boundary layer responds to the shape of the particle. And this when the reversibility of the motion changes. So this is a solution of the zero-order components. The first order steady state streaming flow are given here. So this is the streaming flows, steady state, so time average, so they don't change with time, for two values of acoustic of this frequency parameter lambda. Lambda equal 2 means that the size of the particle is comparable to the Stokes boundary layer vorticity. And another example is when the radius is much larger, or meaning that the Stokes boundary layer is much thinner. You see that then this vorticity, steady state vorticity, they are coming closer to the particle. And this is when this reversibility happens, when this vorticity, these vortices start responding to the details of the nanoparticle shape. And the structure of this streaming flow comes closer and closer to the particle and probes the details of the shape. And the final slide is this angular velocity, theoretical angular velocity, as a function of this frequency parameter lambda. The most interesting effect happens here. At some range of this lambda, we observe reversal of the velocity, where the angular velocity from the counterclockwise changes to clockwise. And what is important, different curves, which represent different value of rotational parameter n, exhibit reversal at different values of this lambda. So we believe that this is the basic mechanism of this reorientation or this reversal of the angular velocity, right? You have your parameters experimental somewhere in this regime where different type of particles, let's say of 3 and 4 symmetry, exhibit crossover from positive to negative rotation at different values of lambda. So if we are in this sensitive regime, then what we can observe experimentally is those reversibilities. At this point, I think I exhaust my time. I would just thank for the collaborations which contributed to this work, and then I can answer your questions if you have. Thank you for your attention.